Yes, ma'am.
Yes, ma'am.
Yeah, so please draw this diagram. Last time we saw it only for cantilever. All right, so finished because I finished drawing. Done. Only Joel's video is on. What about the rest? All right, so I'm going to stop sharing the screen. See, I have the thing solved in the screen itself, but I would prefer to use use the board. All right, so I'm going to stop sharing the screen right now. And I will share this one. Okay, so can you all see the iPad screen?
Yes, ma'am.
Yes, ma'am.
Okay, so now in this case, what will be, this is a simply supported beam which has a hinge support and it has a hinge support and a roller support. So I told you, first thing is you need to calculate the reaction forces on the supports. Okay, so how do you calculate the reaction forces? First of all, how many reaction forces will be there?
Totally 3, ma'am.
Totally 3. Very good. Okay, can you tell me which all?
RAY, RBY, RBX.
Okay, so it will be R. Since the uniformly distributed is downward force, so there will be a force here, RAY, vertical force. Okay, then here it's a roller support. This will be RBY, and there will also be a horizontal. It's a hinge support, so it will have 2 reaction forces. I'm going to name it as say AX in X direction, Y direction. Are you guys clear till now? Okay, see in this unit I'm still in the introduction part. We still haven't learned how to draw the shear force and bending moment diagram. So only if you're thorough with this, we can go ahead with that. That's why I have the extra class, and we missed one class because of the test. Okay, so no problem, we can cover it up, no, not an issue. So okay, if all of you are clear, so here we need to use the equation of equilibrium. All the horizontal forces equal to 0, or the summation of all the vertical forces equal to 0, and summation of all the vertical forces at any point. Now how many points do you see here? A will be equal to B, will be equal to C, will be equal to D, and all this will be equal to 0. You have to understand this moment, because we are assuming that this beam is at equilibrium. All the forces at any point, the summation of all the moments, if you calculate the summation of all the moments with respect to, please remember this, with respect to any point is going to be 0. Okay, because it is at equilibrium. So we can use any of these equations and find. So I am going to use only one. Okay, that is, you can take any point, all right? I am taking with respect to A. You can take with respect to this also. So I'm going to take moment with respect to A. So how many unknowns do we have here? RAY, RAX, and RBY. Is that clear?
Yes,
Joshua,
ma'am.
too many classes today?
Yes, ma'am, a bit.
No problem. It's okay. All right. So if we have, I'll just take 20 minutes class, guys. I know you guys are tired. End of the week. Okay. So we'll just practice this, and then I think tomorrow is a Tuesday timetable. We don't have class, so Monday we'll start fresh. Okay. The main topic for this subject. All right. Many have not come. I'm sure they'll see the recording. All right. So there is only one horizontal force. So RAX will be equal to 0. All right, there's no external horizontal force, so RAX equal to 0. Next is all the vertical forces, so I am going to exclude this because this is not required. All right, I hope you all are writing notes as and when I'm writing. I just have the screen this big. Okay, so sigma V equal to 0. All right, so sigma V equal to 0, how will you solve? What are the vertical forces we have? RAY plus
RBY
RBY equal to
is to 5 into
5.
4.
Very good. 5 into
4.
4. Excellent. All right, so this is one equation. You can write it as RAY plus RBY equal to 20. Okay, now coming to this one. Moment with respect to A. So can you tell me RBY? Let's go from right to left. RBY multiplied by what is the
7.
perpendicular distance? So RBY, the perpendicular we are calculating with respect to point A. So
7.
7. All right. Is it going to be minus or plus? Is it anti-clockwise direction or clockwise direction? You are keeping the beam fixed here, okay?
Anti-clockwise direction.
And it will move in this direction. It will move in this direction because the arrow mark is upwards. All right. So it is anti-clockwise direction, so it will be minus. I hope
Ma'am,
you're
but
able.
it's a resultant, right?
What
It's a
resulted?
resultant force. So how is it going? Moment goes anti-clockwise and clockwise, right?
Yeah, and we are calculating moment only, no?
Okay, okay. I was here, ma'am. I was near the RAY plus RBY. I was seeing
Oh,
that.
okay, okay, okay. Yeah, this is over. Okay,
Sorry,
we
sir.
finished
Sorry,
this.
ma'am.
Let's do the moment now. So RBY into 7. But thanks for asking. Okay, I really appreciate that. So minus R. So I really want anybody, if you get a doubt in your mind, immediately unmute and ask. Okay, because that is easy for me to clear it out, and you don't have to wait till the end of the class, because if you don't clear it then and there, then whatever I teach you will not understand. Okay, so I really appreciate who asked this doubt just now.
Ma'am, yeah, that's sure.
Joshua. Okay, I really appreciate, Joshua, that you asked me then and there. Okay, thank you. Next force is 5, the UDL. So we are going to calculate the moment of the load, uniformly distributed load, 5 kilonewton per meter square with respect to A. So can you tell me the magnitude? We'll do the magnitude first and then we'll go for direction. Okay.
Plus
So load is
5 into
5 into 4. Okay.
into
Then
5 by 2.
who is answering and not able to wait? Okay, okay, Vaishnav. Only Vaishnav is answering. What about the rest? Into
5 by 2.
why 5 by 2?
We should include 1 also, no, ma'am?
1 plus 4 by 2.
Yes, ma'am. Oh,
Okay.
okay, ma'am. Yes, ma'am.
We have to take this distance. You can
Yes,
do
ma'am.
it in your mind also. Take this distance. This is 2 plus
1.
1. So 3 it will come. And the force is downwards. So the moment is going to be positive. Here the moment is negative. So you'll get positive here. I hope it's clear. Are you guys able to understand?
Yes, ma'am.
Okay. Next is RAY. So RAY, the line of force passes through A. So it's going to be no perpendicular distance. So
Hello?
She got stuck, I guess.
Yeah.
Ma'am, your voice is breaking. It's not clear.
0.
Ma'am, the
Yes.
connection went off.
So,
Like, we couldn't hear what he said.
okay,
Ma'am, we
no,
can't hear you.
is it clear now?
Yes, ma'am.
Yeah, we can hear you now, but the
Yeah, I
part
just took
which
a
you
call. I just took a call. That's why it went. So I'll just repeat that.
okay,
So we finished RBY. We finished 5 kilonewton per meter. Okay. Next, what we're going to do is for RAY. So you've learned it in engineering mechanics that RAY line of action passes through A. Okay. We are calculating moment with respect to A.
yeah.
Yeah, so we are calculating moment with respect to A. So if we have to calculate RAY multiplied by perpendicular distance is 0. So this component will always be 0.
0.
Okay, so I am going to not consider this. See, lack of space. That's why I'm writing like this, okay? Please don't mind. Just let me know if you don't understand. So I will take a new page and explain. All right, so equal to 0. All right, sigma MA equal to 0. So with this equation, can you find RB? Can you guys
60
find
by
RB?
7, ma'am.
Yes, ma'am.
Okay. And using RB in equation number 1, this is equation number 2. In equation number 1, can you find RA?
80 by 7, ma'am.
Yeah, so you guys can solve it. I'll give you 1 minute time. Let me check the answer. So you should get RB 8.57, RA, sorry, RBY, and RAY as 11.53 kilonewton.
Ma'am, RBY is
8.57.
8.57.
1 sec. Yep. Yes. RBY is 8.57.
Newton.
RAY, you should get,
11.42.
yeah, 8.57. Guys, the unit is kilonewton.
Oh, kilometer. Okay.
Okay. And RAY is equal to, I can't write smaller also with my hand, 11.53 kilonewton.
Miss RAY is 11.42.
Yeah, it's okay. It's pretty close. No problem. Is it clear, everyone?
Yes, ma'am.
That's right.
So with this, I'm going to close right now. Not close as in close on this preliminary topic. Okay, and I'll give you an introduction of what we're going to do in the next class. All right. Basically, what we are supposed to do is draw the shear force diagram and the bending moment diagram of a beam. Now, if you take this particular, let me take this beam. Okay, and this is A, this is B. At some point, I have an external load at C. Okay, and this load, for example, is 4,000 Newton. Okay, and the distance over here is 2 meters. Okay, now let's take the same beam. This is C, this is A, and I'm going to take some section which is like 1.2 meters away, some section. Okay, and if I cut that section, and you've got a load here, if I cut that section, because of this load, 4,000 load, okay, there will be a shear force at this part, correct? Because of this load, okay, there will be an equal and opposite shear force here. Got it? And you have your reaction force over here,
No,
RA.
but we are cutting it, right?
We're not cutting it. I'm asking you to assume.
Oh,
Okay?
yeah. If
At
we
any
assume it's we are cutting it, so how is how will this force act here? This will in
no,
the
no, no, no. So I didn't mean we are cutting it completely. Okay, we're cutting it completely. But what I'm saying is, if you take this particular point, there will
okay.
be two forces acting. Okay,
Okay.
one because of this and one equal and opposite to this, and this makes it at equilibrium.
Okay.
The whole beam at equilibrium, and that's why it doesn't break basically. Okay, so I'm sorry, I didn't mean cutting. So you take any point. So any point you take, all right, there will be an force.
Equilibrium.
Yeah, so there is a so this at this point, any point on the beam, there are two forces acting, one because of the load and the other equal and opposite load. So on this side, you have one force, and on this side also, on the right and left, both the sides, you've got a shear force. Okay, so keeping this in mind, we will be drawing, okay, we will be drawing the shear force diagram of this particular object. Okay, so what do you mean by shear force diagram? You have an, one second, you have x-axis and you've got y-axis. All right, x-axis will denote your length of the beam. Y-axis denotes your shear force at each point of the beam. Okay, so now you have the x-axis. This is full length is not given. Okay, let's take this as 1. So full length is 3 meters. Okay, I'm going to divide C, B, and A. Is that clear? Okay, C, B, and A. All right, and let's take another point here. Okay, as D, this point. So can you tell me what will be the shear force at point B? There is no shear force on B, correct? So it's going to be 0. Got it? All right.
Yes, ma'am.
At point C, 4,000 is the shear force. All right. At
Yes, ma'am.
point D, now when you take, see, when I'm considering the B point, I am considering only the right side of the drawing. Okay, so there's nothing on the right side, no other forces, so it's 0 here. At point C, you take this part. Okay, what are the forces acting on this part of the beam? It's 4,000. So you mark point 4,000 here. So I'm going to name that as C dash. All right. Next is, one second. Where is it? Next is point D. When I take point D and I consider only the left, right side of the drawing. Okay, so what are the forces? Now, if there is a force on the 4,000 is acting on C, the same force is acting on this part as well. Okay, so at D also, it's the same 4,000. So if you notice here, there is a shear load here. Okay, so at D also, there is a 4,000 load. So that is D dash. Okay, that is D dash. Now come to point A. What is the shear load acting here? If you take only this part of the uh, beam, I've taken point D here. If I take some point here, E, for example, I take a point E. For example, this is E. You take only this part of the drawing. Again, at this point, it is 4,000 load acting. All right, so here also it is 4,000 kilonewton acting.
Ma'am, for point loads, it will be equal at every point, right? According to
Yes,
this.
yes, but this load is acting over here. All right, so when we see at any section on the left side of the drawing, okay, it will be the same load acting. Here it is 0.
Ma'am, what about direction, ma'am?
Direction is downward direction.
Downward.
Down, yeah, we'll take it as positive. All right, because see what is happening here is you're taking a reaction force. All right, you're calculating the reaction force here, which is an upward force. That's what we are marking it here. Okay, so let's take it as positive, positive, positive. At this point also it will be positive, but just before this point it will be positive, and but at point A there is a reaction force equal to 4,000, so it will become 0. So this is our shear force diagram. All right, are you guys clear? One second. So in the next class, we will be seeing in detail how it will be. See, it's not going to be like this. It's going to be in this direction because here there is absolutely no load. All right. So this is my shear force diagram, which is a positive load. All right. So in next class, we will calculate. We'll take a simple diagram and I'll teach you the rules of how to take the positive and negative, okay, and how to draw the shear force diagram for bending moment, for bending moment as well, shear force and bending moment diagram. Okay, so we'd start with cantilever, then we'll for both the loads, point load and UDL, then we'll go ahead with simply supported, and then we'll go ahead with overhanging beam. Okay, but are you guys clear about how to calculate the reaction forces?
Up to this clear, ma'am, but this only, ma'am. What you have
This
said,
don't
ma'am.
worry about it. I will explain it again in the next class.
Okay,
Ma'am,
Is
ma'am.
that
like on point D, like the shear force is 4,000 and the reaction force is again 4,000.
yeah?
Then the total like the
So
total effective
reaction
force.
force. See, listen. In point D, right?
Yeah.
Point D, there is no support.
Yes, ma'am.
There is no support. So, but there is a reaction force.
Yeah.
All right. The acting force is 4,000. All right. So we
Yeah.
take, so actually you saw how we calculated the reaction forces. So RA here will be equal to positive 4,000. Correct?
Yes, ma'am.
It will be positive 4,000. So this is going to be actually negative. Yeah, actually the diagram should come like this. All right, never mind. I will explain to you exactly how we're going to take a proper problem and explain. I'll explain everything in the next class. But what I want you to understand today is that what is a shear force diagram and what is a bending moment diagram. For a beam, at every point, there is a shear load because of different loads which is acting on the beam. Okay, and this shear load can be represented in a graphical format, and that is called as shear force diagram. Okay, the sign convection and how to calculate for each point I will tell you in detail, teach you in detail in the next class. Okay.
Okay, ma'am.
Yeah.
Yes, ma'am.
All right. So yeah. So thank you for joining in for the extra class. So we will see you guys on Monday.
Ma'am, I had one question as well. Like,
Yeah.
if if it had been a uniformly distributed load, then reactions occurring at D and E would have been different, right?
Yes. Yes. You're right. So your if for example if there is a UDL here, your diagram will change like this.
Okay.
Okay. Because it's a varying load, right? So it will
Yes,
not
ma'am.
be same throughout.
Yeah.
Okay. We'll see it in detail in the next class.
Okay.
Okay.
Thank you, ma'am.
Yeah. Thanks, guys.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Most
Thank you,
welcome.
ma'am.
Bye.
Bye,
Bye,
ma'am.
ma'am. Have a good day, ma'am. Bye, Ashwin. Bye, Benison. Bye, David. Bye, Shane.